There is a difference between these two gene sequence clips. The first are the first few codons in a wild-type HBB gene, and the second is a slightly mutated version of this gene. And this tiny difference is actually the reason for a deadly inherited blood disorder, SCA or sickle cell anemia. SCA is one of the many diseases that can actually be caused with these kind of gene mutations, but luckily scientists have actually created a cure for this, and it's called CRISPR. So what actually CRISPR does in the real world is it helps bacteria cut and recognize viral DNA. So basically, in an oversimplified way, when viruses attack, bacteria actually produces RNA matching this kind of virus DNA, and then it pairs it essentially with the Cas9 protein to now cut the viral DNA. This essentially allows people to both deactivate a gene and also just completely replace a gene. And to go deeper into this, I built a paper model. There's going to be a couple components of this model. First, the target DNA, the DNA molecule containing the specific target gene to be edited, and then there's going to be guide RNA or gRNA, an RNA molecule that binds to the Cas9 enzyme and directs it into the target gene by matching its sequence. And then Cas9, a nucleus enzyme that cuts the DNA at the target site, specified by the guide RNA or gRNA. And then there's going to be donor RNA, a template provided to enable precise editing of the target gene. And then random nucleotides, DNA building blocks that can be randomly inserted at the cut site, potentially disrupting the gene. So first, I just printed out some copies of the actual components of the CRISPR model. Then I got some clear tape to actually attach it to the model, and finally some scissors to actually cut it out. So first I started off with actually cutting the model of the CRISPR enzyme. And then the tabs which will hold the RNA in place. And then I taped them onto the Cas9 protein printout. I also cut out the rest of the components. So to start off, I added RNA1 into the Cas9 protein model. And then I took guide RNA1 and attached it to the Cas9 enzyme. And then I cut the DNA1 sequence by the dotted lines. So that essentially just showed basically how CRISPR actually works. But using this process, scientists can actually do a couple of things, the most common being two different choices: non-homologous end joining or NHEJ and homology-directed repair or HDR. So basically, after cleaving target DNA1 from earlier steps, you can simulate the cell's attempt to repair the break using NHEJ. So essentially, NHEJ is a repair mechanism that often introduces errors like random insertions or deletions. These errors can disrupt the gene, effectively inactivating it. Scientists use this method for gene knockout experiments to study gene functions. So basically, a simple way of showing this is to just put the random nucleotides between the two pieces of DNA. Next, I wanted to look at homology-directed repair or HDR. So just a quick overview of what actually HDR is. It's basically a more precise repair mechanism that uses a homologous DNA template to guide the repair of the break. Scientists can actually provide this template to include specific edits, and HDR can introduce specific changes at the cut site, such as replacing, adding, or correcting DNA sequences. So to actually model this, I repeated the earlier steps, except now using guide RNA2 and target DNA2. So basically, HDR uses a template, for example in this case donor DNA, for precise DNA repair, allowing scientists to correct mutations or add new gene sequences. In this case, we got rid of the 4-nucleotide deletion of GAGT and inserted it into the original sequence in the mutant gene. This method is commonly used for gene editing in applications such as fixing disease-causing mutations. Yeah, so that's pretty much it for this time. I hope you enjoyed the video. P.S. Here's the tutorial that I actually followed. I hope you come and watch my other videos too. Bye.